Picking back up with part 2 of 6.2 day 2, the method of Frobenius. We're restarting from a little bit where we left off. You can see from part 1, the indexes down below, k equals -1 and k equals -1. We need to truncate those, work those out so that we'll have a k equals 0 for each of our sigmas, for each of our sums. So as we do that, I think you can quickly see what's going to happen as you allow k to equal -1. You're going to have a 3 c sub 0. And the -1 here plus 1 is just going to go away. You'll have an r. And then, of course, you're also going to have this, k equaling -1. So -1 plus r is going to be over here as well. You'll have this x to the -1. But as we generate the same thing over in this regard, you're going to see that we're going to also have another c sub 0. And this time a -1 plus 1 is just going to wipe out. You're going to have an r. And once again, you're going to have this x to the -1. Now, once you have that, the really neat part about it is that all sigmas are in fact going to be going from k equals 0 up to infinity. And we're going to be able to, thank goodness, do some combining and work some things out. We're going to do that in just a moment. But drawing attention just to what we have here at the start, you're going to notice that we have an x to the -1 and a c sub 0 for both of these. And what's going to happen is we'll have our c sub 0 and x to the -1. But then what's going to be left? Well, we'll have a 3r squared minus a 3r, because I'm going to distribute that 3r to both of those. And here we just have a positive 1r if I factored out as c naught x to the -1. So we would be left really with a 3r squared minus 2r, and that would be really our coefficient of x to the -1. Now, at this point, I do want to call attention to the fact that whatever is out in front of any power of x really is going to have to equal 0. So it's tempting to look at the c sub 0. Remember, c sub 0 is meant to be a constant, not necessarily equal to 0. What we're going to do, though, is we're going to say, look, 3r squared minus 2r, that must equal 0. I could factor out an r and very quickly solve and get r equals 0 or r is equal to 2/3. It's not difficult to solve in that regard. We're going to get back to that in a moment. But for that coefficient of x to the -1 to guaranteedly be 0, this is what's going to have to happen. What's kind of nice now, though, is now we come back up and we're going to say, hey, looking at these sigmas, the 3 sigmas that we have here, maybe we could go ahead and join them all together and see what's about to happen. You can see pretty much that there are, in fact, 2 terms with a 3 c sub k plus 1, well, with a c k plus 1 down below. I'm going to make these in blue. Trying to see what is in common here. We've got that. What else do they have in common? They both have a k plus 1 plus r. That's kind of cool. And they both also have an x to the k. So that's quite a bit that they do have in common. Now, what they don't have actually in common is that 3 and the k plus r. So maybe just making a note, here if we were to distribute, we'd have a 3k plus 3r, And over here we'd have just a 1. So if I factored that c sub k plus 1 and x to the k out, what would be left? Well, we'd have a 3k plus 3r. We'd also have this plus 1. So I'd like to do a little bit of simplifying in this regard. We're going to say, look, if we pull out what we just said that we were going to, if we were going to pull out the c sub k plus 1 and also the k plus 1 plus r, we also had our x sub k right here. And then we could even, deal with this minus c sub k, x sub k in here. That's what we have inside of sigma. Wow. Well, at this point, I hope you can see that we could have just as easily said, because we're joining our two sigmas together, we could look at these x to the k's and pull them out of that parenthesis and just say, look, they're in common, so we could just pull that out over here. So what you're hopefully seeing is every coefficient of x, whatever is in front of x, of course, must equal 0. That means what we have right in here, all of this stuff, that's going to have to collapse to 0. What we've been doing, whether we had singular points or not, we're going to keep doing this all along, is we try to solve for the higher subscript. We're going to solve for a c sub k plus 1. And to do that, you could see that we'd have to add a c sub k to the right side. We'd have to divide by what is in front of c sub k plus 1. And right now, we are well on our way to moving forward. You see, here's the thing that we're going to ultimately be looking at. You see, right now it looks very much like what we were doing earlier when we had ordinary points. But we've got this extra issue of the r's. And tell you what, we're going to have two cases. We have case 1, where we could say, look, r could be 0. We also have case 2, where we're going to say, look, our r could be 2/3. And that r is going to definitely impact this equation that we just solved for, because r's are in them. So we're going to take this c sub k plus 1, here's case 1, we're going to say, let's look at this formula. If everywhere where we see an r, it's going to just go to 0. And that's the nice situation. It doesn't get much nicer than that. Your r's completely disappear, and you're left with a much simpler form. What else do we have? Well, we've got this other issue, and I think this is the one that gets way more intimidating. We can say, well, we can go back and take our c sub k plus 1, but now wherever we have an r, we're going to plug in 2/3. And I think it's the first parenthesis down below where we might be quite pleased to see that the 3's are going to cancel, and that's going to nicely clean up. You can see you'll just have a 2 plus 1, leaving you with a 3 down below. 3k plus 3, I should have said. However, it's here where maybe things aren't quite as nice. The 1 is 3/3. 3/3 plus 2/3 is 5/3. And I think it's right here where, understandably, kids can be maybe less than thrilled to see that formula. Well, listen, regardless how ugly the formula is, you could definitely still generate terms. But I'd like to do something a little bit different. I'm going to factor out a 3 from my first parenthesis. You think, why are you doing that? answer, so I can distribute that 3 to the other parenthesis. Look, nobody likes seeing these fractions in there. So if we can help ourselves out a little bit, we should. What's going to happen? Well, we'll have our k plus 1 down here, but as I distribute, I'll have a 3k plus 5. It's at this point, guys, where right now we're really back to what we were doing earlier, where in our first section, we decide to look at our smaller index and let k equal values that are as small as possible. So here we could let k equal 0, for example. We'd be left with c sub 1 would equal c sub 0. And of course, down below 0 plus 1 would just be a 1. 3 times 0 is 0. You're just left with 0 plus 5. That's just going to be a 5 down below. Let's let k equal positive 1, and then you can see that we'd get c sub 2. We'd get c sub 1 all over. Well, 1 plus 1 is a 2, and 1 times 3 is 3. 3 plus 5 is 8. 8 times 2 is 16. But remember, you found c sub 1. C sub 1 is c 0 over 5, c naught. 5 divided, the 5 is brought down by the 16, and 5 times 16 would get you actually an 80. So if we'd let k equal a 2, you know, we could keep doing this. Maybe we'll even start right here. You know, we of course would have c sub 3. That would equal c sub 2 over, well, 2 plus 1 is a 3, and 2 times 3 is 6. 6 plus 5 is going to be 33. 6 plus 5 is 11, which times 3 is 33. Pardon me, talking a little bit ahead of myself. But c sub 2 is c naught all over 80. And bring the 80 down next to the 33. Well, we'd get a 0. 8 times 3 is 24. Carry the 2. I guess that's 2,640. And hey, look at that. We'd definitely be able to generate a term here. So this is where we need to be aware of what is happening. We could say, look, we might remember that we had x to the r times our sigma. And we don't want to forget that. We certainly don't want to forget the x to the r. So r here was 2/3. You might remember us talking about. So, you know, as we work this out, we'll have x to the 2/3. And what was that? Of course, it's going to be x to the r. And as we work this out, we'd say it's c sub 0 plus c sub 1x plus c sub 2 x squared plus c sub 3x to the 3rd. You get the idea. You know, we'd have c sub 0, and then we'd have c sub 1x, but what was c sub 1? It was c sub 0 all over 5. And then we come over here, we'd have c sub 2 x squared. C sub 2 was c sub 0 over 80. That's what we'll have for our x squared. What's in front of our x cubed? Well, c sub 3. Got that big 2,640 down below. And you can see that that's really one of our solutions. Technically, it was our second case. I guess you could even call it y sub 2. But, you know, that's the case where r is equal to 2/3. We should also consider what's going to happen in our other case. And we're going to actually make one last video to finish that up.